Hello everyone. During this lecture, we are going to continue with chapter 1. First, I want to talk about curvilinear coordinates. So far we only discussed Cartesian coordinate system. Now we have 3 dimensions x, y, z. But for this course, we are also going to deal with cylindrical and spherical coordinate systems, especially for cylindrical coordinate system, which is very common in this course. Okay, so make sure you are also familiar with this curvilinear coordinates. If we look at a cylindrical coordinate system, okay, so we know we do not have x, y, z. We have r, theta, z. Z is the same. So r is the square root x squared plus y squared. The theta we know is related to the angle, so which is arctangent y to x. Okay. Now let's have some practice and also better understand the cylindrical system. So for this practice, let's practice on how to write first expression. Okay. Also can review our stress definition and also can let you get used to the cylindrical coordinate system. Okay, so there are 3 examples. So let's look at first one. So for this one, we can see the first is this direction line by the fluid is in the theta direction. So this is theta. Okay. And also for r, remember it's square root x squared plus y squared. So basically it's the direction is from the center, right? Point towards the cylinder wall. Okay. So now let's write the force. So we know stress is defined as force divided by volume. Then force can be written by stress multiplied by the area. Okay, so let's start with the area. So if you look at this area here, so we know this is the shape, right? Since it's small, tiny, so we can consider it as a square. Suddenly, for the square, the area is A multiplied by B. So we know for this case, this length is in the direction, right? We know for this small element, B here is DC. Then what about the length? A here, the arc. So for arc, okay. So let's say this is the radius r, and this is d theta. Okay. So the length of the arc is r d theta. So then we know the area for this case is r d theta dz. So now let's put the stress here. So for stress, we have to identify the 2 subscript. So start from right towards left, remember? So the subscript on the right indicates the direction of the first momentum flux, right? So we know for this case, the first is theta direction. Now we have to determine what is on the left. Since we are talking about first, remember the subscript on the left, given the meaning, right, of in which direction, right, the area perpendicular to. So we know for this case, this area is perpendicular, look at here, to the R direction. So now we know the subscript here is R. Okay. So this is probably a difficult part, okay, for you to decide. Again, the one on the right to talk about the first momentum flux direction. So this one on the left shows the momentum transport direction, or the direction which is perpendicular, right, to the surface of the force, right? The surface of the force works on our impact. And also, there's a negative sign because along the positive R, the velocity decrease. But for now, don't worry about the sign. Okay, so make sure you can get to the area and the top correct. So now give you a couple minutes to practice on your own. So there are two more, so please pick one. Okay, don't worry about the sign. So focus on the first and the area. Okay, so let's move on. So you can see the answer here. Okay. We know viscosity depends on both pressure and the temperature. For pressure, in general, the viscosity of fluid increases only weakly with pressure increase at a given temperature. Okay, so not significant impact. Okay, when it comes to pressure, but the temperature impact affect viscosity greatly, and also it depends on liquid or gas we are talking about. The trends are actually opposite. If you look at liquid, with the increase of temperature, the viscosity decreases. But for gas, especially the low density ones, if you increase temperature, the viscosity actually increases. Okay. The difference is here can be explained by the intermolecular distance differences, okay, between liquid and gas. So again, the reason is because the intermolecular distance. And also the viscosity can be determined empirically, okay? So here let's talk about reduced viscosity and reduced pressure, okay? So this is important for us to determine the viscosity empirically. So for reduced viscosity and reduced pressure and also reduced temperature, we basically define it as the value of viscosity, pressure, or temperature divided by the values at critical point. Okay, so C here stands for critical point. So basically, PC, TC, MUC are the values at a critical point. So why we're interested in the reduced values? Because for reduced value, okay, MOR, PR, TR, they are all unitless, all dimensionless. Okay, so which can be beneficial. Okay. So how do we determine viscosity? Okay. So we have to get both MUC, MUR, right? Remember, MUR reduced viscosity equals mu divided by MUC. So then we know mu equals MUR multiplied by MUC, right? So to get MUR, in general, we need both PR and TR, okay? And also to get MUC, we also need PC and TC values, okay? So once we get MUC, MUR, then we can calculate mu viscosity. Especially how do we go from PC, TC to MUC, there is equation. Okay, so this is an empirical relation. Okay, so this is how PC, TC, and MUC are related. So big M here is molar mass. You also need beta M, which is molar mass. Okay. So to get MUR, okay, we're going to get the value from the table of figure. I will show you. Okay. So now let's go to our slides. Okay, so this is the figure or type I'm referring to. So this summarizes the pressure and temperature dependence of viscosity. So for this graph, so make sure you understand what are you looking at. Y axis is reduced viscosity, remember? They are unitless, just numbers, right? The x-axis reduced temperature, again, unitless. And also this one has something to do with pressure. So you see multiple curves here, right? So for individual curve, they have the other values have the same, taking under the same pressure, okay? So for each curve, okay, it represents one pressure condition. So that's why I say for this curve is actually reflect all three, viscosity, temperature, and the pressure. So if we look at the pressure influence on the viscosity, so we know this is the direction of temperature increase, right? So we can say this is the direction of the pressure increase. So we can see if we increase, take a look at liquid here. If we increase temperature, increase pressure, we can see the temperature doesn't increase significantly, right? If you look at temperature influence, so we know this is the direction temperature increase, this direction of pressure increase, right? So if we look at liquid, okay, we can see with the increase of temperature, okay, if we keep the P consistent, okay, increase the T, we can see actually the mole decrease, okay? If we look at the low density gas, so we can see with the increase of temperature, the mole increase, okay? So that's why I say if you just look at this graph, it also gives you the information. So again, P doesn't, in general, does not significantly impact viscosity. So we can see the viscosity increase only slightly with the increase of pressure, right? For temperature, for liquid, increase the temperature causes the decrease of viscosity, okay? For low density gas, you increase the temperature, you increase the viscosity. So now let's do some calculation. Use μC and μR to calculate the viscosity. So for this case, we need to estimate the viscosity of nitrogen gas at 50 degrees Celsius and 850 for atmosphere. The molar mass is 28.0 gram per mole. We have PC and TC. Okay, now let's see what we have. So we have T, which is 50 degrees Celsius. So we have to convert it to Kelvin, right, which is standard. So to convert to Kelvin, we multiply by 273.2. Okay, so we get Kelvin. We have P, which is at 54, right, ATM. And also PC is given. So we know PC is 33.5 atmosphere. Okay. We also know TC is 1.26.2 Kelvin. Okay. So now we know to get mole, we need both mole R and mole C, right? So for mole C, we know we can get from TC and PC. So we know for mole C we have the equation. So let's calculate. So 7.70 multiplied by molar mass, which is 28.0 gram per mole. Okay, so the index is half, and then multiplied by PC, which is 33.5. We know the unit is ATM. The index here is 2/3, and then multiply by TC, which is 126.2. We know the unit is Kelvin. the index here is negative 1.6. Okay, so if you use these units, you are going to get micropoise. Okay, so the answer is 189 micropoise. If we change it to poise, we know from micro we are talking about 10 to the 6th power, right? Conversion factor, so which is 1.89 multiplied by 10 to the negative first poise. So we have mu c now, so we need mu r, right? So from mu r, to get mu r, we need tr and pr, okay? So to calculate TR/PR, which is easy, right? So we know PR is P equals by PC. So we know is 854 ATM divided by 33.5 ATM atmosphere. You see the unit cancel, become unitless, which is 25.5. So now let's calculate Tc. So we know Tc is Tr equals T divided by Tc. So we know T is 273.2 plus 50 Kelvin, right? Tc, which is 126.2 Kelvin, you see K cancelled. So we get 2.56. Okay. So now we get TR/PR. So we need to go to the figure of the table. We just discussed. Okay. So go back to this. So you see TR, right? PR, then we can get mu r. So start with T. So we know T is TR is 2.56. So this we know is 2.5-ish. Okay. So we extend this line, and also there's different curves we want to choose the one we use based on what pressure, right? Remember, each curve is taking at a specific pressure. So the PR is 25.5. So this is the pressure curve for 25. So we know it's about here, right? So then you extend T to cross here, then you extend it to get the mu r. Okay, so let me find something. Okay, this is going to be helpful. So let's say this is 2.56, okay? So you extend the line, and because the pressure is 25.5, so it should be above this curve, right? So let's say it's here. Then you extend it to here. So we know it is probably 2 point something, okay? So let's use the number from the textbook, okay? So textbook estimated to be 2.6. So then So we know mu R is 2.6. Okay. So then mu equals mu C multiplied by mu R, so which is 2.6 multiplied by 1.89, 10 to the negative first, right? The unit is pounds, so which is about 4.9, 10 to the negative first pounds. Okay. So this is how you estimate the viscosity using reduced temperature, pressure, and viscosity. Okay. Now let's move on to the last section of chapter 1.7. Okay. Go back to our lecture notes. So we know during 1.1 and 1.2 we talk about the molecular transport of momentum. Momentum can also be transported by the bulk flow of fluid. So for this type of transport we call convective transport. Okay. So to give you more information here, for molecular transport of momentum, molecular transport of momentum. We know which is internal. It involves three physical properties. Okay. Viscosity, K, and D. So K is thermal conductivity. Okay. D is the diffusion coefficient. So we know for fluid mostly we focus on the viscosity. Okay. So if we talk about convective transport, which only involves one physical property. Density, rho. Okay. So for convection, we're talking about the bulk flow of fluid, right? So mostly we're talking about the external influence. Okay. So now it's necessary for us to consider both molecular momentum transport and also convective transport. Consider the sum set up as 1.2 when we have a generalized Newton's law of viscosity, right? So this is the sum set up. So if we look at this center point, and then we consider 3 mutually perpendicular planes, right? Okay. We know momentum is mass multiplied by velocity. Okay. So mass divided by volume, we know we get density, right? So you multiply volume here and then divide 1, multiply 1, so it's still same. So then the left becomes density, then you have volume multiplied by velocity. Okay. So now if we look at the momentum flow rate per unit area, what's this? Momentum flux. Okay. So remember, when we talk about rate, it is something divided by time. If we talk about flux, it is rate divided by the area. So see for this one, we are talking about momentum rate and then per unit area. So we are talking about momentum flux. So basically, this part, this is the momentum flux. Okay. So if we look at the momentum flux, okay, perpendicular to the x direction. So if we look at here, so for this case, this is the situation we are talking about. We can see we are talking about the momentum, right? Flux, right? Which is related to the area, right? And this area is perpendicular to the x direction. Okay. So then, if we write the equation, so for this case, we are talking about the momentum flux, right? Related to the area. The area is perpendicular to x direction. So basically, we are talking about momentum flux in x direction. Okay. So for this case now, we now this equals momentum, right, divided by the area, which is perpendicular to x direction or along the x direction. So the area we know is perpendicular to x. So we can say what we can get is density, right? Here, which is mass divided by volume, right? And then we multiply a volume, then divide by area perpendicular to x, and multiply by time, and also multiply by velocity. So what does this part give you? So the volume divided by the area perpendicular to x. So this actually gives you the length in x direction. And the length in x direction divided by time give you what? The velocity in x direction. So then, for the momentum flux in x direction, or the momentum flux related to the area which is perpendicular to x, so we can get the expression is rho Vx V. So this is what we can get. So same thing, momentum flow rate for the y plane. We know we are talking about the momentum in y direction, right? And the unit area is perpendicular to y. So similarly, we can get momentum flow rate for the y plane. Okay, rho v y v for z, rho v z v. Again, for the v here, remember it's vector, so use both face. So for velocity, one unique thing is pay attention. If we already define the direction, we don't need to use both face anymore. That's why for Vx, Vy, Vz, we don't need to use the both face. Okay. So this is what we have for now. So each of these three vectors have three components each. So if we consider x direction, when we describe this, we talk about the momentum right along the x, or the momentum impact the area which is perpendicular to x direction. But the momentum can be from x direction, or y direction, or z direction, right? So that's why for each of these, it has three components. So total we have 9, okay? So for this secondary order tensor, we know tensor does secondary order. We call this tensors what? Remember we are talking about connective momentum transport, right? So for this tensor, okay, all 9 of them. So we use row v to indicate. So for v, remember vector about face. Since this is general, we do not define the actual direction velocity. That's why about face for both. So row v. So for this tensor, we call connective momentum flux tensor. Okay. Connective okay. So to summarize, we know we have total 9 components. So this is very similar to 1.2, right? The table we saw. So again, we have x, y, z. So these are direction normal to the shaded surface. So again, how do you understand x, y, z? Easiest way is the momentum is along the x, along the y, along z. Or we are talking about the shaded surface, which is perpendicular to x, to y, to z. Okay, so to make this clear to you, so we talk about x, y, z. Okay, so for this table and the table, when we talk about the generalization of Newton's law of viscosity, so for both table the same, so the x, y, z. How do you understand? So basically, along x direction, along y, along z direction. Or we are talking about the area perpendicular to x, perpendicular to y, perpendicular to z. Okay. This is how we understand x, y, z. So now we know, for x we know we are talking about the momentum flux, which is along the x, or impact area which is perpendicular to x direction. So we know that's the subscript on the left, right? Remember the subscript on the right defines the direction of the momentum itself, right? Okay, so from left to right, left talk about the momentum itself, direction, and the second one, which is on the left, describe the impact of the momentum. Okay, so these are easier way to understand. So now, you see for this case, it actually has 3 subcomponents. If the momentum itself from x, it's rho vx, vx. If the momentum come from y, it's rho vx, vy. Okay. If the momentum is from z, then it's rho vx, vz. So let's add 2 here. So for momentum flux, the one we have discussed so far, tau, y, pi, we know tau is viscous, pi is molecular, and rho v is what? Convective. So for all these three tensors, we now have two subscripts, right? So we always read from right towards left, okay? So the one on the right, it describes the force or momentum itself. Okay, so for example, the momentum flux is from x direction. Okay, the one on the left talk about the impact. Okay, so we talk about the impact. So it's an impact what direction, or the area perpendicular to this direction. Okay. So now I think it's probably a better time to summarize all this. Okay. So for example, if it's tau yx start from right, then we know the x. If we talk about first, we know the first is x, right, applied in x direction, or the momentum is from x. And then if we talk about first, we know the first impact x direction, right, or applied to the area which is perpendicular to the y, okay? If we talk about momentum, so we know for this case, the momentum is from x, and it's along the y direction. Okay, so we know momentum is transported in the y direction. Now to summarize all what we have discussed so far of chapter 1. So we start with viscous momentum flux tensor, which is tau, right? Then we talk about the molecular momentum flux tensor, for which we have to consider the pressure impact, right? So now we know molecular momentum flux tensor, okay, pi, again, bold, right, equals P. Remember, P is scalar, not bold, okay, lowercase and italic, but we do have a delta, Kronecker delta, okay, then plus tau. Okay, so this is molecular momentum flux tensor. So we know for convective momentum flux tensor, which is rho VV. So if you combine molecular and convective momentum flux tensor together, we call combined momentum flux tensor. So which you and molecular momentum flux tensor and convective momentum flux tensor together. So then, for the combined momentum flux tensor, which we use symbol phi, again, dot phase, right? Molecular, we know is pi, plus convective, which is rho v dot v. And also because pi equals p delta, Kronecker equal delta, then plus tau, then rho v v. Okay. So this is combined momentum flux. Okay. Now let's practice writing the components of phi in terms of other tensor components. So if we look at first one, phi xx, we know phi xx equals pi xx plus rho vx xy, okay? And also pi xx equals p delta xx, other than plus tau xx, then rho vx vx. Since I equals j, we know delta equals 1, right? So this is what we have. Okay? So now, give you a minute to write phi xy. Give you a minute to write phi xy. Okay, now check your answer. This is phi xy because delta is 0 because I is not the same as j, right? So this is what we have for phi xy. Okay. So now let's put phi xy into words. So what's the meaning of phi xy? Unfortunately, for textbook, which is wrong. Okay, so it is corrected in the newer version of the book. Okay, so do not make sure do not use your textbook for this. So how do we describe phi xy. Okay, so phi xy, if we describe it, remember from right towards left, so we are talking about combined or total, okay, momentum flux. So we use combined momentum flux, or you can use total, so either way is fine. So we are talking about the total momentum flux, right? And also we know this momentum flux is from this direction, right? Y, okay? So this is the first component. And the second component, for this Y we know it is Y momentum. Right itself is from Y. And then the X, we're talking about the impact. So that's what we know the momentum is transported in X direction, or positive X direction. So then if we merge all these three into one sentence, okay? So it describes the total or combined flux of Y momentum transported in the positive X direction. We know the area it impacted, which is perpendicular to X. Okay. This is all for today's lecture. Okay. See you next time.